Fluke Biomedical Cufflink Part 2. Okay, we're just going to show doing some of the different performance tests on a non-invasive blood pressure unit using the Cufflink. These tests you're looking at are basically it's a manometer test, a leak test, and what is called a pop-off test. So basically that we're looking at these tests are under the PRESS menu or pressure menu, and just they're listed as leak test, manometer, and pop-off. Using the cursor key controls, let's just go to manometer and hit enter. And now with this system fully set up, attached with a cuff, we can then put the Dynamap in a diagnostic mode by holding the minutes down and then the power and letting it go, and that will now make your cuff pressure or your mean arterial display read basically a manometer pressure. So with the Cufflink you can turn the pump on, turn it off, release the pressure, print the data, and also zero the transducer. And if you want, you can just simply unplug this, vent it to atmosphere. We're reading 0.5 millimeter of mercury. And if we wanted to, we can just zero that out for the most accurate. So now we're reading 0.00. So let's turn the pump on for a little bit. It's inflating the cuff and the other related accessories. Bring it up to a value, let's say around 200. Then let it just dynamically settle. And we read about 215, 214 on the Cufflink, 218 on the Criticon. And so it's just a verification that the transducer is calibrated rather well. And I guess if you wanted to, you could do a more calibration adjustment on that, but for purposes of this demonstration, it's adequate. Now we can go in, release the pressure, open up the line, goes back to 0. Then we escape out of the manometer test. Use the cursor to go up to leak test. Hit enter. And now what we're looking at is a target pressure of 200 millimeters of mercury. We want to inflate it till it gets over 200. Once it does, it stabilizes the reading, and the analyzer will display how much the pressure changes over a 1 minute time period, and it'll display it as a leak rate or a leak factor on the analyzer. So we just turn on the pump. Probably best bet, before you start this test, reset the diagnostic mode on the Criticon, because that will time out by itself. We want to make sure that that runs for a full minute. Okay. Bring the pressure up, something over 200. And I've got it at about 203. Just waiting for it to stabilize. And now we can start the test. And now it's just reading the pressure and looking for the pressure changes. Then after 1 minute, it'll give you a leak rate. So again, it's a real good little test, making sure all your accessory items are in good shape. Also, too, it's a good test on the Cufflink itself, making sure that the internal tubing is intact. So again, we're reading about 194 and 195 on the unit. So to do this test before, you'd have to have a manometer and a stopwatch and a pencil, and you have to be watching it. So what we've done is fully automate that test for you, make it a lot easier. So these tests, along with the dynamic tests that this device can do, will also be able to control that via the med tester also. Okay, so the 1 minute time has expired, and we're reading a leak rate of 5 millimeters of mercury. So with that, it's be a matter of looking at the specification for the device as it's specified by the manufacturer for
this
acceptable.
device.
Yes, exactly. So, again, making sure that the NIBP device does have this type of a diagnostic mode. What you might find out too is that in some cases when you're making these tests, the NIBP monitor has its own leak rates built into it and its own diagnostics. So if that's the case, you can use the Cufflink in its own digital manometer mode where you're monitoring the pressure here, and you can actually then run the tests using the device. I know many of them do this. I know the Philips do. Medical Data Electronics, they actually run those tests automatically, and that they will do the static pressure checks and also the pop-off test and the leakage manometer and pop-off tests can be done, with those devices directly. But you can always use this to verify what pressures are being generated actually within the system. Okay, as I said, the unit does reset itself once in a while, periodically. So we've done the leak test, done the manometer test. Now the other test is one where it's called pop-off. And pop-off basically is that the compressor in the unit is running, and possibly if there's a problem with it, you want to make sure that there's a relief valve in the unit so that it opens this cuff line to atmosphere, because you don't want to sit there and cut the circulation completely off on the patient's arm. So to run that test, we'll just reset this again. Okay, we're ready to go. Use the cursor again here to go down to pop-off. Hit enter. And now we just turn the pump on. And you can see the pressure is going up. At 250 it's going to begin flashing because that's the maximum pressure range. It's going to keep on going. Okay. So it did pop off, and you're looking at a value of like about 360 millimeters of mercury.
Wow.
So just making sure everything does work. But with that, it's something that they should go before 400 millimeters of mercury. Okay, so that again we've covered the basic dynamic simulation, and we've covered the different static tests of manometer, of leakage test, and also pop-off. So that with this, those are the things you're going to need to do in the basic, operation of the analyzer, testing your units. What I would like to do is just go back now and show you a couple of the more detailed features of the unit for dynamic simulation. So right now it's the same setup, everything's as we had before. Have the analyzer turned on, and just go back up to the main menu of the Cufflink. And again, it automatically defaults to the the dynamic simulation, and as we call it, the Atoms family. And with that, after it goes through its little power-up routine, I said just hit enter twice, and that automatically gets you to a 120/80 dynamic blood pressure. And now, again, we're ready to go for 120/80. So just hit our green button there for start. I want to get a baseline pressure reading. Okay, it's now deflating. Our unit is generating the pulse like your arm would. And so we're looking at 115/78. I think our young coding unit's competing. So we're getting a little baseline of a normal blood pressure. Now, for example, that if you wanted to simulate a higher blood pressure, you could just go in and select the next one up, which would be like 150/100. Or, if you'd like, you can take the same waveform, and then you can go in and adjust the envelope. And with this, you can shift the envelope. You can shift it positive or negative. So let's take the 120/80 blood pressure waveform and shift it positively, let's say 10 millimeters of mercury. So now 120/80 is 130/100. Over 90, excuse me. Over 90, excuse me. So now we're all ready to go. So hit enter. So whatever we got before, we should tack on about 10 millimeters of mercury. So this would be a very good way for testing the alarms on these monitors. And it'd be a lot tighter control. So if you're looking to do the alarm test, it would be easier to use it this way than trying to use it the other way. So it basically popped on 10 millimeters of mercury.
126 instead of 130. Yeah.
And again, too, with that, adjust the envelope. You can go both ways. You can then go in and increase or decrease it. Instead of by positive 10, you can make it negative 10. And also, too, that the output on this is in the adult Adams family is set up primarily for doing the standard adult cuff, standard adult. Now, if you're going to try to run and do a large adult, or basically the large thigh cuffs that they use sometimes, probably will still work fine, but you may just need to increase the gain or the amplitude of that pulse, because there's you've got a much larger artery in your leg, so it's going to be a much larger, higher amplitude pulse. So with it, you can go into the gain mode, as we have right here, and just simply increase that gain. And yes, about 110, 115% probably would be more realistic. And you would then be able to test your larger cuffs. Also, too, that if they're having complaints about the monitor where, well, I had problems getting a blood pressure. Well, what you could do is you can then lower the amplitude of the peripheral pulse and just see what the sensitivity level is of the monitor. So instead of using 100% normal, use, let's say, 75% or 60%, and that would simulate someone that's in shock or they've got a very weak pulse. So their heart isn't beating quite as well, and they say, well, this monitor works great on healthy people, but when I put a sick person on it, hey, I have problems with it. So let's simulate a sick patient and then lower the amplitude of the pulse. And that's always a good point for comparison, too, if you're looking at new NIBP monitors, or you've gotten some in from the field and you just want to see how well they work. just run that control and see how well they do measure the blood pressure. At what amplitude does it truly measure the pulse properly. I know that during the development of the Cufflink, we did run into that a few times. A couple of companies that, if you were healthy, it worked all day long, but if you were in shock, it never would work.
Good explanation.
Okay, so that gives you the ability to adjust the pressure levels dynamically, so you can take our 120/80 and add pressure to it, or take pressure away from it. And you can also run either a strong pulse, a normal pulse, or a weak pulse, simulating different patient conditions. So imagine too, if you're testing athletes or whatever, you can make sure that it can work there too with the higher pulse amplitudes. Great. Any questions or any thing you have questions on either non-invasive blood pressure or the Cufflink?
It's really simple.
That's very straightforward. We've done the adult work. Just to let you know that if you are going to be testing any of the neonatal capabilities, we also have a mandrel that is cut for the 3 most prevalent sizes of neonatal cuffs also. So that something that is close to a normal pediatric down to definitely small neonatal. And there are smaller ones than that, but these were just more of the 3 most typically used units. And with that there is a separate menu under that for the adult. We have Adams Adult, and we have Adams Neonate. So then it's basically the pulses are much narrower, and also they're about 12% of the total adult amplitude. So very, very small, very, very small pulses. So as we can adjust the pulse amplitude in the adult, we can also do it in the neonatal. I guess since this is a fixed volume pulse, it is important if you do use the larger cuffs, you can increase the amplitude of the pulse to make it, approximately the same relative amplitude as when it would be coming out of the standard adult cuff-equipped system. We also do have an arrhythmia mode. That's an adult arrhythmia mode. There's just a series of a few, I won't say, life-threatening arrhythmias, but there are just basically.
What's different here?
With this, it's a matter where if you're in a condition where your heart isn't beating, normally, then maybe that you've got like a premature beat, or if you've got it could be a premature normal beat, or a premature ventricular beat, or an atrial fibrillation beat, where the interval between the R waves are different. We then can simulate that too. So it's most NIBP devices should have the ability to work with basic arrhythmias. So, and it's a matter where if the patient has ECG problems beyond what's in here, typically that they would have a indwelling cardiac pressure line put in, and they'd be measuring the blood pressure directly. Yeah, if you want, we can just go through and I can show you. There's a normal rhythm selected, and then there's a premature atrial contraction, and we're going to be able to hear that where it's different from what we were simulating before. Before, we had a nice, strong, solid pulse. It was beating 80 beats per minute all day long, all working out very well. This one is going to be a premature beat that's going to occur. I think about every 8 to 10 beats, it's a premature beat is programmed in the unit. And with it, what's going to happen, it's going to take longer for the monitor to measure that blood pressure, because the technology that's used in the monitor, it's based on a technology where it's a stepped deflation on the cuff pressure. And what it will do, after it initially pumps up to the peak and it begins to deflate, it'll sit at one static pressure level until it has 2 beats that are very close to the same amplitude. Once that happens, it said, okay, I've got a good pulse.
Clear beats.
Let's go down some more pressure.
Yeah.
Get 2 more good beats. Go down 2 or 3 more
Okay.
millimeters of mercury. Get it again, and just keep them going that way. So what you're going to see is the total test time with an irregular rhythm is going to take should take a little bit longer. And if you have a patient who has a really irregular rhythm, that monitor won't even measure a blood pressure. It says, hey, this is too much variation. I don't know what's going on. Put a pressure line. Put a pressure line into him and said, I'm good, but I'm not that good. So let's look at what last time we ran the test. Oh, I've already changed menus, but let's just run it and see what the test time is. Okay, I'm all set up to do a premature atrial contraction. So just hit start.
Start.
Okay, once it starts to deflate, you're going to be able to hear that premature beat. So you just so it's like a mist. It sounds like a mist beat. And as you can see, the steps are much longer.
Yes, you're right.
Because it says, hey, what's going on here? But this is the nice part about the Cufflink. You have that cuff pressure waveform, and you can say, well, yeah, it's a weird beat, it's an arrhythmia. It'll still measure it, but it's going to take it longer. And it's going to take it longer because of that irregularity. And you can see the irregularity in that cuff deflation curve. Now, it still works very good. You still get a reading of 115 over 79 for 120 over 80. And you get a MAP of 92, which is, might as well be normal. That's very good. But as you can see, the test time, total test time, is 31 seconds. It's a long time to have a cuff on your arm, but with this patient with that type of a problem, you would normally see that amount of time. Now we can just go back and do a normal one, normal sinus. Okay, now this is the same pressure, but with a good ECG, 80 beats per minute. So I'm going to start it again. Now we're looking to compare, number one, the step deflation, see what those steps look like, and also what is the total test time of what you've done.
She's a healthy patient.
So test healthy people all day long here. So you can see the test time is only 19 seconds. So very good tool for looking at the operation of your non-invasive blood pressure units, and by looking at the cuff pressure waveform, things are a lot more uniform. It's a much faster deflation because it's gotten a better pulse and a more constant pulse. Now, if you test other types of devices, still works with it. Call in Medical. They're right here in Texas. They're now owned by Omron. They just bought them a little while ago. Some of the Collin Medical series equipment, the 8800 series, and the newer Pressmate series of units, those use a linear deflate. So instead of a stepped deflate where it measures 2 pulses, then deflates, it does a linear deflate with a needle valve. And with that, it just simply outputs the pulses as it goes down. We may not be as accurate with those because it is a pressure that's going down a lot faster, and what will happen is we'll measure cuff pressure at one point, but by the time we generate it, the cuff pressure is already going down a couple of millimeters of mercury. So the cuff pressure that we've output is actually referenced back to an earlier cuff pressure when it was higher. but it's within about 10%. That's typically what you're going to see for these kind of devices. Also, some other technologies, CIS is another company, and instead of measuring on the deflate, they measure on the inflation. But hey, we're still good.
Yeah.
Because with our system that we measure the pressure in the cuff and output the pulse that's proportional to what the patient's doing at that cuff pressure. It doesn't matter if it's going up or going down, we generate it. So again, a very good test tool for non-invasive blood pressure. Okay, so covered the adult, the neonatal, and some of the tricks. So, and again, too, if you have any questions while you're out there using the device, you'll be very happy to, take your phone call and say, "Hey, I'm trying to do this. What in the world's going on here?" Be very happy to assist you. Most of the units I've seen that you've got are very conventional technologies, and I think you shouldn't really have much problem, dealing with it. Half the problem is just getting the cuffs set up, but I think you've got the adapters and everything else that you do need here. What I've covered is what the analyzer does do, what it's intended to do, but I think probably too the important thing to do is tell you what it doesn't do. It doesn't work with any of the cuffs that are designed for auscultatory technologies. That would be ones where that they would have the actual microphones in the cuff, and they're actually looking for a sound where the cord cuff sounds going through the patient's arm, the blood coursing through the artery, the sound of the artery that the blood would make going through the artery. Typical brands on that there are some common medical units that are used in treadmill areas. There's SunTech. It's another company that makes it. But when you plug it in and there's more than just a pressurized line, they've got some type of an electronic connection, then
Usually
it probably won't work. We did have an auscultatory option for this a long time ago, but it was for the IVAC model 4200. That was something that's been dropped quite a while ago. And the IVAC 4200 was designed to work primarily as an auscultatory type. And it actually has a little force transducer in the cuff that did look for the wall movement. But if it didn't get a good signal from the sensor, it would default to an oscillometric method. So if you possibly get any of those in, you could still test it with the Cufflink. I doubt you would, because it's been dropped a long time ago, and it was only sold in the U.S. So it's not really set up, for running internationally at 220. I don't think they even made a 220 volt version.
I can rely on it, and I use it as a very important tool in our calibration procedures.
Yep. So, like I said, you can even use the other modes, the digital manometer modes, for other things. If you have any of the rotating tourniquet systems or the Jobst systems, or actually anything that's a pneumatically driven system, you probably could use the Cufflink for testing it. Okay, so any other questions or anything? Or
Thank you.
You know everything I know about it now.
Hi, on, Mike.
Okay, all set.
Yep, good.
Okay, Mike Riles, Fluke Biomedical, or at Medicend in Dallas, Texas. We're going to be doing a basic review of the basic functionality of the Index 2 SPO2 simulator. And this is the model Index 2 XL, and it's the one with both optical and electrical simulation capabilities. Okay, with this basically that you're able to either electrically simulate the SPO2 signal, and you can do that by eliminating the optical sensor within the system, so that you're just testing the basic electronics of the device. Or if you're looking to do more of a complete system test, you can also do your testing via the optical finger on the front of the instrument. Obviously, you'll only use one at a time when you're doing the work, because that you have to synchronize the operation of the index with that of the monitor. So it can only use one active input interface at a time. Mm-hmm. Right now we are running the electrical simulation. We're having some problem with the optical, but the electrical simulation is looking like it is working quite well. So from a basic operational perspective, once you turn the device on and you've hooked in the electrical simulation cable to the instrumentation amp on the Nellcore. Right now we're using one of the earlier Nellcore series monitors, and with that then we're doing it, I said, direct electrical simulation. So you don't have any of the variations or any of the difficulties with using the optical finger, and it is a more repeatable test. So if you just have the equipment to test, this is a good way to do it. If you're, though, looking at troubleshooting a system that's in the field, it's best, to verify with a reusable probe. In the case of the Nellcore, the DS100, that would be the better one to use. The calibration curves for the MaxAL is very similar to that of the DS100, so we shouldn't really have any major problems. Okay, so we've got the electrical output attached to the back of the index, hooked up to the Nellcore input. First, and one of the more important things, is you go in to the menu, main menu number 2, F4 make, and just use the up-down keys to find Nellcore. There's no enter button, so as soon as you do select it, that is active, and then just escape out of it and push F5 or the last key until it comes up to the simulation key, and that's the F1, and now that will give you direct access to the manual simulations. And default start-off value is 96% saturation and a rate of 75. Yeah, with this right now, that it will go directly to that, but it does have to see a signal from the oximeter to advance into this. If by chance that this were, not attached, you would get a indication, no red LED, no IR, no infrared LED, and is pressed to escape. Now if you try to get into the menu, it won't sometimes let you go in, but if you hit it a couple times, it will let you into that menu. But you still have to connect it up to make a good connection to get the analyzer to the simulator to recognize a probe. So default, it's SPO2 96 is the 96% is the default value, and with a rate of 75. And lo and behold, looking at the Nellcore monitor, we do have that reading directly on the screen. Mm-hmm. So it's working out well. This version of the index, the N100 and 200 series, that it that was what the model was that we were working with when we designed the index. That was in the earlier models that were available from Nelcor. Most of the newer ones, the OxyMax series and that sort of thing, that we are working on something as an upgrade to this that'll give you some more capability. But for the optical simulation, we are compatible with the newer OxyMax technology. We're working on a new electrical simulation cable that will give you electrical simulation capability with the OxyMax technology. With electrical simulation, you need that smart chip in there, and also we're running some different shielding in the cabling. It's a lot more of a sensitive system, so we need to connect up the shields for both the two light sources and also for the detector. Okay, with this you're able then to adjust saturation levels. You can go all the way up to 100, and usually this is an average responding system, so it's going to take a few beats for it to catch up. And so everything is working quite well here. Basic calibration, you're looking at from 70% to 100% is really the calibration range on these. Yes, you can run at lower values, but as it is with many of the pulse oximeters, those are uncalibrated levels. The display and simulation will wrap around, so if I can increase it again from 100, that will wrap it back around to 35% as the very bottom. And with this one, you're looking typically at about a 2%. From 70 to 100, usually under 70%. Many of these devices, the monitors themselves aren't really specified. But it does give you the ability to do some just general testing on the devices to looking for a basic response. In most cases, you're looking for normal, which is going to be high 90s, typically 97 to 98. And if you're looking at anything, under 80, you're talking serious, pneumonia or chronic obstructive lung disease, COPD, those sort of things where the functionality of the lungs, it's greatly degraded. So we can go through the, different saturation levels. And with it too, that we can also the saturation levels and then also a range of heart rates. So, like I said, we can just keep on going, but more than we cover the physiological range. So 25 to 250 beats per minute. And so the monitor is well able to keep up with that range of settings. Okay, so basic performance testing on simulation for both the saturation level and also on heart rate. And with the two, you're looking at something that's going to be a very much a quick check on this thing. This is a pulse oximetry itself is a indirect, non-invasive measurement, and where you aren't measuring the actual blood itself for oxygen saturation. You're looking at a secondary measurement, that of light going through both the pulsatile and non-pulsable blood, and looking at the ability of this indirect method to give you a reading. So with it won't be as accurate as the laboratory work, but obviously it's not as invasive to the patient. So applications are primarily for for trending, looking for variation within the saturation of the patient on a long-term basis. Okay, in addition to that, we also do have capability of some preset selections, and that with this, that we do have different pulse strengths, different heart rates, and different saturation levels. So it just defines the range of possible patients that you would have in the field. So a normal patient, but with a bit of a lower heart rate, but good saturation. And then this is a weak pulse, so you're looking probably at about a 50% pulse strength, and also a lower saturation and a little higher heart rate. So with this, then, we are looking at simulating more worst-case conditions. And the rest of these are well defined up in the manuals, but here you're looking at bradycardia, so a low patient heart rate and a low saturation level to go along with it.
Bradycardia.
And hypoxic, or a low saturation level, which we definitely have someone who's having some problems here with a very low saturation level. And then little babies, it's a little bit of a lower saturation level with a much higher heart rate. And a basic adult tachycardia with a low saturation level. Geriatric, again, a lower saturation level, and then it's a compromised pulse based on comes down to basically, in layman's terms, hardening of the artery, so the waveforms themselves are lower amplitude, and also with a lower resulting saturation level. And obese, same thing, lower saturation level with a bit of a higher heart rate. And then back to your normal. So all the menus do wrap around. So that you got the basic ability, for adjusting it, for saturation and rate, and also you can look at a couple of different patient types by going through the preset menu structure. And again, with this, you can go in and put in some ambient light levels, and just look and see how well that the unit will work with different noises that are being combined with the signals. And again, this works both with optical and the electrical simulation. So with these, you're looking at two different line frequency values, 60 hertz and 50 hertz, and then there's just a sunlight, and all it really is flooding the both optical inputs, so that basically it's in many cases with older monitors that if you were to have very high levels of light coming in when the infrared and red were supposed to be coming in, that would give you an R calibration value that gave you always an 85%. So that's one thing I always look for. If someone says, I'm having a problem with my monitor and it's always reading 85%, if that's the case, I say, get them out of the sun, and actually shield the site where the sensor is on the person's finger, put them inside or whatever, and then see what type of measurement you do get. But that condition we do simulate it, so this is something where depending on the monitor, you could then actually pull up that artifact alarm and say, hey, high sunlight condition, it will give that response. That is one of the selections for the newer Oxymex, where it does look at that condition. Okay. We're not going to really mess with the TLC at this point. In upcoming versions of this, that's being redone, so you won't have to really mess with it. What now? The TLC is basically it's a transmission level control or light control. It goes both ways. I've heard it called both, but it's a level control, and that sets the DC operating points of both the visible red and the infrared. But it does them both at the same time.
For the same thing.
Yeah. Now, if you wanted to change these a little differently for each of the colors, you couldn't do that. So the earlier versions of this, in the M version, had that capability. You could independently set the infrared light levels and also the DC levels, infrared and visible red, which is what you really need to have. So we're reverting back to the old method. It's much better. Some of the other monitors, we're running Nelcor right now. With the known-in medical, possibly if you're running that with this now, might have a couple of problems because it's going to show as a low pulse amplitude. That would be about the only time I would really even recommend you using the TLC. Right now the TLC on this one is set for, it's like 3,500. That's out of a maximum of 4,096. That's the maximum range, 0 to 4,096.
12 digits.
Yep. Yeah, we went right past the 512 and this kept on going here. But with this, though, you're able then to set at those levels. The default for the non-in medical, it got set too low. So I can go in here. Yeah, it's preset here at 1,000. So if you're running non-in medical units, I would just simply go into this menu and run it up to about almost somewhere around 3,000, 2,700 to 3,000. Right now, unfortunately, you'll lose those values once you escape out of the menu, but once you escape out of the simulation menu, you will. As long as you're in the simulation menu, you'll be okay. But if you go beyond here, you will lose it. But I would look in at kicking it up. But like I said, anytime you do have problems or you're seeing some issues with pulse amplitude, just go into the TLC and see what the numbers are. And if they're low, which would be anything from 500 to about 1,200, and just go in there and jack them up until you see, about 3,000. And all that's doing is basically just giving you a stronger signal by giving you less tissue, less simulated tissue. The lights have to go through, so you're putting lower resistance on the light sources, so you will get a higher amplitude signal. For right now, go back into the make. Okay, we're back into Nelcor now. Okay, so we've gone through the basics on those. And here we have a couple of different sequences. This is kind of nice. These would be basic alarm tests where you can go into oxygen and you can then go into you can start it. So basically, you can go through. You can start it. You can start a test, and then go in and change it. And you wait until you can see how long it takes for the system to catch up and to make a measurement. Then once it does make a measurement to 98, which it now has, you can push that, and that will give you the response. So that is basically for those tests. You can run oxygen saturation rate, pulse amplitude, then also an asystole type alarm. So if, like when you do have a measurement and you've got the alarm set on there, you can then test, having the patient actually go into an asystole condition. Okey-dokey. Auto, we're going to more so cover with a med tester. And just a couple other different options. Yep, go ahead. These are more for programming, so I don't want to really get into those at this point. And configuration. Also, you have the ability for doing a basic probe test. This is with the electrical simulation version. Just pop in your probe, and then you've got the ability to do a resistance on the wire. And that gives you the pinouts and the different resistances. So then you can just flex the cables and see how well they are working. Then two, you've got, actually they go in and actually bias the LEDs and the photodetector. And then in here, there is a photo mode, and this is actually where you're actually pulsing the lights. So we can see the visible red, but not the infrared. And then we're also monitoring how much is getting to the photodetector on the other side. So if you put them closer together, of course the numbers go higher. And with these, we're going to be including a piece of acrylic plastic in here so that you can run this kind of a test with an optical load. But you can see typically numbers over 2,000, you've got a good probe. Okie dokie. Okay, we're running out of tape.